Out. Okay. Hello, everyone. My name is Ahmad. I'm a postdoctoral researcher. It's a pleasure to welcome you to today's seminar organized by the Green Construction Research and Training Center at the University of British Columbia. I'll be moderating today's session along with the center's manager, Bora. We are delighted to have Professor Dimitrios Lignas with us today. Professor Lignas is a full professor and the chair of the Civil Engineering Institute at École Polytechnique Fédérale de Lausanne, or EPFL. A key aspect of his research lies in the development of advanced models and approaches that leverage multi-scale experimentation to advance our understanding of the ultimate limited states that trigger structural collapse in steel structures. Professor Lignas joined the PFL in 2016 from McGill University, Canada. Prior to that, he was a postdoctoral researcher at Kyoto University and Stanford University. He holds degrees in structural engineering from Stanford University and civil engineering from NTU Athens. The work of his group has been acknowledged through several prestigious international awards, including the 2022 Raymond Rees Research Prize and the 2019 Walter Huber Civil Engineering Research Prize, among others, from the American Society of Civil Engineers. As a member of the project team too, he was responsible for the revision of the steel and composite steel concrete structures in the second generation of Eurocode 8. As an associate member of ASC 41, he developed seismic assessment models for steel columns and beam-to-column connections that were adopted in ASC 4123. There's also led the Task Group 2 or Working Group 9 of CSAS 16 on the recent revisions on the seismic provisions for steel moment frames. Today's presentation, as you can see the title, promises to be rich in content for sure. Professor Lignas will present for approximately an hour, and we'll follow that with a Q&A session. Please note that the session is being recorded with the presenter's content and will be available for viewing afterwards. Without further ado, I'd like to hand over the session to Professor Lignas. Professor Lignas, the floor is yours.
Okay, well, thank you very much for the nice introduction, Ahmed, and thank you everybody for joining this session in the morning. I apologize if time doesn't work well. Here is about 6 p.m., but hopefully this presentation will be interesting. I'd like to first thank the Green Construction Research and Training Center for the kind invitation to present this work, as well as funding coming from the Swiss National Science Foundation, as well as Nippon Steel Corporation for pretty much some of the, or most of the work that you're going to see in this talk. I'd like also to thank the actual people who did the work. So I'd like to thank Dr. Skiadopoulos, who is now a postdoc at Stanford University, Dr. Rina Masso, who is now a professor or associate professor in Kyoto University, Ahmed Delkadi, who is assistant professor at the University of Southampton, as well as Dr. Albano Souza, who is a senior scientist here in my group. So today's presentation is a presentation that will mostly focus on steel moment frames. And as we know, this is a popular structural system due to its versatility and increased ductility, energy dissipation, and because of moment resistance through the energy dissipation from beam-to-column connections. And just a quick overview. As we know, like a moment resisting connection after the Northridge earthquake, primarily based on work done during the SAC project, will be assembled by using, let's say, mostly a strong panel zone design where energy dissipation will be localized in the beams. And through local buckling, we anticipate to take pretty much the energy released by the earthquake. Now, when it comes to the welded connection, usually here you are going to use a backing bar that we're going to remove and back gouge, perhaps reinforce with a fillet weld here to ensure that the fracture potential of the connection has been reduced, at least based on what we knew or we know till today. Now, for capacity designed steel moment resisting frames, what we call in Canada ductile moment frames, the intended dissipative zones during earthquake events would be more or less at the beam ends. And as I said before, assuming that the connection details are done in the right way, then plastic deformations will localize in the beams. And after flexural yielding, we would anticipate to see local buckling within the dissipative zone. Or if you're looking at the base of the columns, these are fixed end columns. In this case, we should anticipate to see plastic deformation near the fixed end that could potentially followed by local buckling, as we see here in this photo. Now, if we look at this from a structural safety point of view, this would be the anticipated behavior. But if you are looking at this from, say, financial perspective, then these damage that I show here would potentially have to be repaired, or if the building essentially ends up having a very large residual, then we would consider the potential for demolition. So we've done, in fact, loss assessment in several steel moment resisting frame buildings, and we looked at monetary losses due to repairs after an earthquake. And in this graph, this is an indicative graph that you would essentially get the expected losses as a function of the seismic intensity. And here you see that for seismic intensities that would be what we call a design level earthquake, losses are going to be governed by repairs, structural repairs, as well as repairs in the non-structural content. But then when the seismic intensity increases, you see that the dashed green line essentially demonstrates that demolition may be a critical factor prior to the case that you may have collapse controlling losses. But that would be under a rare event where the spectral intensity, seismic intensity would be very large in this case. So if we look at essentially what this means for a steel moment frame as part of a building, if we're looking at repairs, essentially you're going to get to do structural repairs because of local buckling at the fixed end that I showed earlier. And if you're looking at the connection, you're going to have to focus around the dissipative zone that is mostly related to the beam that experienced flexural yielding and eventually local buckling. So if we judge this sort of way of dissipating the energy from a structural repair standpoint, obviously this is not going to be very economic because this has to be fixed in the aftermath of an earthquake. Now, instabilities also, if you're looking at instabilities, would have an implication on degradation and potentially structural collapse, because if I look at here a test from a few years ago at the defense facility, a moment frame due to the mode of deformation would tend to localize deformations in the bottom stories, and potentially for seismic intensities related to modest events, we would get more or less the anticipated mechanism with damage in the beams as well as damage at the base of the column. But if strength degradation kicks in because of the instabilities, then usually the beam here that is marked with orange is going to degrade. That would create redistribution in the system. And in this case, you would anticipate to have larger moments in the columns that for, let's say, larger or rare earthquake events could potentially lead into plastic hinges in the columns, and then eventually you could have a structural collapse. Now, because of this, engineers, or at least people like me, who are interested into estimating the probability of structural collapse for moment frames as well as other systems. And as we know here, this is a graph that I usually use from Professor Kravinkler. If you look at one ground motion and you're looking at the seismic intensity here, and you're plotting the seismic intensity versus the maximum story drift ratio, if the system doesn't experience degradation and you worry about second order effects due to gravity, then usually this could carry on for very large intensities. But if you're dealing with a degrading system, such as the one I showed earlier because of the local buckling or other types of geometric instabilities, then usually these curves turn flat, and at a certain intensity here, you would experience dynamic instability. So what happens is that if you want to estimate the probability of collapse, you would have to focus in this region here. And usually that can be done if you use models of certain sophistication, so that you can actually simulate the influence of strength degradation on the overall structural performance. Now, these models have been around, and if some of you use these models, I think you might have run into my name, especially on steel structures. Could be concentrated plasticity models, or could be fiber models, or rarely continuum models with reduced fidelity. And what happens here is that, if you look at these models, usually you will have to kind of predict relatively well when would be the onset of strength degradation. But based on our experience with this from test data as well as simulations, generally this point is associated with fairly large variability. So that variability would be transferred in these models that we use for predicting probability of collapse. So now the question is, if you are really predicting the probability of collapse accurately enough so that you can minimize the risk of collapse in degrading systems. Now, so at some point, at least when I was working on this, I kind of started thinking, where should I go from here? And because most of my work relates to moment frames, I was thinking, is this really the right way of doing this? Or there could be different ways that we could consider and perhaps rethink about the design process, or maybe rethink about technology and so on, so that we can stay away from instabilities and potentially reduce uncertainty and potentially also reduce repairs. So when I was in California, I've heard, this sort of, or I've read somewhere this sort of interesting quote by Professor Ed Wilson from UC Berkeley, where essentially he was saying that instead of trying to develop more complex models to capture the variability of structural response, pretty much like the models that you showed before, that somewhat relate to the early part of my work as an academician, we should be designing structures that are less sensitive to uncertainty. So, so that made me think about how could we rethink about the seismic design process of steel moment resisting frames, so that we can achieve such an endeavor. So in the rest of the presentation, essentially, I'll be focusing on two things. The first one is if we can identify or rely on alternative dissipative mechanisms than those of the current status quo, where with those we could potentially stay away from instabilities or at least delay them and potentially reduce model uncertainty that we would have in this case. So, the talk is a bit provocative, but hopefully at the end of the presentation, you would be, let's say, inspired, and you would also agree that there are ways that this can be done. So I will start first by identifying alternative dissipative mechanisms, and I would like to stress the beneficial aspects of shear yielding that were introduced firstly by Professor Krawinkler during his PhD thesis back in the 70s, done with Professor Popov and Professor Bertero, where at that time he or they were looking at essentially the potential behavior of panel zones or moment-resisting connections that exhibit high inelastic behavior in the panel zones. And what we know from this work is that panel zones usually exhibit shear yielding, and the behavior can be extremely stable, even at very large inelastic shear distortions. And then if you look at the overall behavior of the actual connection itself, you see that for very large drifts in the range of 6%, we get no degradation when the panel zone participates more or participates a lot more into the energy dissipation of the joint. Now, this several years later has been also contrasted by work done by Professor Mike Engerhard from University of Texas at Austin, where here you see conventional behavior of a beam-to-column connection designed with an elastic panel zone, which is code compliant. This is what we would do today. And then when you're looking at the story shear behavior versus story drift ratio, you see that this exhibits degradation because, as we discussed in the introduction of the presentation, local buckling will kick in at the steel beams. Now, this would happen in the range of 2 to 3% drift, which could be a drift that you may see at the design level earthquake or more frequently in a maximum considered earthquake. Now, as part of the same test program, like they conducted the tests where the panel zones were designed to be inelastic, and you see that they can carry on like very large deformations. And notice that for the same level of drifts that we talked about before, the behavior of the joint is actually pretty stable without noticing any sign of strength degradation. And you can also see this visually from this graph here, because if you notice the regions nearby the panel zone on the beam side, you see that you don't get local buckling in the beams. So then one could ask, so why then not allowing for shear yielding? Well, the truth is that, if you push, or research shown that, if you push panel zones to behave in a highly inelastic manner, then in the region that is known as the intersection between the flange and the web, this is a region of high stress and strain demand, and then there could be the potential of having fracture here. And obviously fracture is not desirable when we do this. But then the question is, if fracture does occur, one question I would ask myself is, what is really the drift that this is actually going to happen? So for this, we've reviewed or we put together test data from Porth-Northridge connections. And in fact, you can download this data from our website here. That essentially, this is an interactive website that you are able to filter data on connections. And if we set up the requirements to be, let's say, post-Northridge connections, you can essentially see out of these connections how many, in fact, experience fracture when we push the panel zone to be highly inelastic. And in fact, when we look at this data, what we see here with this graph is that this graph shows what the probability of failure or fracture would be for a given story drift ratio and a given panel zone shear distortion for certain designs of the panel zone that we may be interested. So here you see that, for instance, if the panel zone is code compliant, if you are at 4% drift, the probability of having fracture is going to be fairly minimum. And if you basically push the panel zone to go to 10 gamma Y, which is not allowed right now, you see that the probability of having fracture, if you review all these tests available in the literature, assuming that you are respecting everything else in terms of weld requirements and so on, you see that the increase is fairly marginal. So then the question is, if it's fairly marginal, if we really have the tools to be able to allow for inelastic design in the panel zones and kind of relaxed requirements in the beams, so that would mean what are the missing aspects that we have to be able to accomplish such a design. So one of them essentially relates to limitation of the current design models to be able to leverage shear yielding in a design context. And the current codes would use a trilinear model to design the panel zone, where essentially you will have to predict Vy and Vp here. Vy is the CR at which the panel zone exhibits uniform distribution, uniform shear yielding. Vp would be the plastic resistance of the panel zone, assuming that it reaches 4 gamma Y. And what we see from these models is that essentially the elastic stiffness of the model is only considering shear deformations. And this is why when you actually compare the predicted stiffness from these 100 tests that we reviewed versus the measured stiffness from the 100 tests we reviewed, we see that there are deviations between the predictive model that we use in design when it comes to stiffness, and these deviations could be in the range of 20%. If you are comparing, for instance, with the model in the AASC provisions or the previous model in the Canadian provisions. But the same happens if you use other models available in the literature. Now, things get more complicated when it comes to strength. If you are looking here at the graph where it normalizes the plastic resistance of the panel zone versus that measured from the 100 tests, you see here that when you get into panel zones with column geometries that the thickness is in the range of 70 millimeters, or let's say above 40 millimeters, then the panel zone model will overpredict the strength of the panel zone, and it could get as high as 40% relative to what was measured in this sort of 100 tests that I showed you. So our first task here in this, what I'm showing today, is to first have a fresh look on the problem to develop a better panel zone model so that we can be able to leverage it in the design of actual moment frames. And essentially the way we are basically doing this, or the way we did this, is by using continuum finite element analysis with models such as the one that you see here, where we were able to predict relatively well what is happening in panel zone geometries in these 100 tests, but also a lot more geometries that we looked at so that we can understand what is really happening in the panel zone and under what conditions. And you see here in this illustration that this finite element model is able to predict well, more or less, this test data in the literature. But also you see something else, that when you use the current AISC provisions or the model that is in the current AISC provisions, you see that this model overpredicts stiffness and overpredicts strength. So this is why relying on panel zone shear could be an issue if you are not predicting strength correctly, because then you are not tuned the strength accordingly. So to fix the problem with stiffness, essentially we developed a model that is able to trace not just shear deformation in the panel zone, but also the contribution to bending because of bending in the flanges. That could be important, especially if you're dealing with very deep beams that are characteristic in North America. And with a simple model here, you are able to capture both the flexural and shear contribution into the elastic stiffness. Now, if you compare the predicted stiffness of this model versus the one measured from the 100 tests I showed, you see that I can reduce the error in the stiffness relatively well. And that would be because I'm able to actually capture the flexural deformation in the flanges, especially for panel zone geometries with very high aspect ratios. Now, with regards to strength, again, looking at the mechanics of these panel zones, we kind of split the data we had available into geometries where the beams would be say in the range of W30 by 108, and the column would be in the range of W24 by 131. So you would have a panel zone geometry here that the aspect ratio is perhaps close to 1. And what happens here is that in columns that flanges are not relatively thick, if you look at here the flange contribution, you see that the flange contribution is fairly minor. But if I'm looking at columns where the thicknesses are relatively high, you see that in this case, the flange contribution into strength, it would start be very important. So for this reason, we developed a new model that relies on mechanics and essentially captures the contribution of the web as well as the contribution of the flange. And essentially the trick, it goes into these coefficients, AW effective, I call it, A flange effective, I call it, where with explicit analytical expressions, you can capture the contribution of the web and the flange much more accurately than what's in the literature right now. And if I show you here, for instance, some of the comparisons I was showing before, where I'm comparing what would be the prediction on strength on VP versus the one measured in experiments, and I actually compare with what I'm getting with the proposed model, you see that even in the range of like very thick flanges, I am able to reduce my error by 40%, and I can predict strength within a 10% error accuracy, regardless of the column flange thickness. Now, I think one of the biggest contribution of this is that this model has now been adopted in the newest revision of CSA 16 in the seismic design of ductile moment frames. And essentially, you can predict now VP with this model that you will probably see there, which relies essentially on this work. Now, so assuming I have a model, I can tune the strength of the joint better. Now, a couple of other things that we were interested related to fabrication detailing. And in particular, when I'm looking at the way we are fabricating welded joints, as I mentioned before, in this region, usually we use a backing bar that essentially we have to complete the complete joint penetration weld. And because of the detail here, I have locations of potential flaws that I'm marking here as L1, L2, and L3. Now, assuming that you are using new construction materials that we use today, L3 should not be a problem because this is related to through thickness properties of the flange. So essentially, the focus is on L1 and L2, that these would be potential flaws because of the welding process. And this is a snapshot from pre-Northridge connection. Usually we like to remove the backing bar here because what happens behind it is that you may have a flow that is running across the flange. And if the flow is large, then this is essentially a region where the risk of fracture is going to be very high. So what we've done here is that, again, we kind of use simulation and we kind of tried to use simulation-based design where we could essentially explore the possibility of not removing the backing bar after the weld is completed to essentially minimize two things. Inspection processes, because if you remove, then you have to inspect and make sure that the flows are sufficiently small. Otherwise, you have to back gouge and repair. And obviously, we wanted to have a better quality also in this region so that we can ensure that, we minimize the fracture potential, particularly in the case that we increase the energy dissipation in the panel zone. And obviously, such an endeavor requires testing, but before you do tests, it's also good to do simulations. And here we use the conventional fracture mechanics-based simulations, where we looked at what would happen in the joint here if the conventional backing bar remains in place. And in this diagram, you see that for a pre-Northridge connection, when your J integral, which is a conventional fracture mechanics metric, matches what you get from the weld, essentially at around 1.5% drift, assuming the variability also on the weld electrode, you see that you would get more or less fracture if you leave the backing bar in place. Now, we worked with an alternative geometry of a backing bar where essentially we introduce a bevel, and you see here the bevel that basically you bevel the backing bar in a certain angle. And then instead of starting the weld right on the beam flange, you basically start the weld outside of the flange, right where the bevel starts. And if you actually repeat the simulations by introducing the bevel here, you see that now fracture potential could be the case, but at drifts that are much larger than what we anticipate in a maximum considered event. And in this case would be larger than 6%. And this is a pre-Northridge connection, okay? So we thought that this is actually promising, since the fracture potential for pre-Northridge connections would be reduced by 6 times by simply introducing a bevel in the backing bar. And with that, we went on to conduct tests where we wanted to construct a beam-to-column connection the way we do today, but we wanted to achieve stable hysteretic behavior through an alternative dissipative mechanism, which is CR yielding in the panel zone. And at 4% drift, we would like to have at least 15 gamma Y in the panel zone, so highly dissipative. We want to prevent beam local buckling prior to a lateral drift of 5%, so that A, we can minimize repairs in the beams in the case of modest drifts, and B, we could alleviate instabilities or delay instabilities, so that would naturally increase the capacity of the system against structural collapse. And the third one relates to weld technology, and in particular beveled backing bars that are left intentionally in place, so that we can examine if this really does work, because that would be a very interesting thing from a fabrication standpoint. So here you see the panel zone geometry, as well as the beveled backing bar that was left in place prior to welding, including the bevel I showed before that was actually that we used in the simulations that I showed in the previous slide. So we did the beam-to-column testing of interior joints here, but in a horizontal fashion, where you see here the two beams that were loaded with 2 actuators that you see at the beam ends. And the column here, that was a column with relatively thick flanges, like 70 millimeters, was subjected also to axial load. That was 20% of the nominal axial resistance of the column. So I'm going to show one of these tests based on the AISC loading protocol. And here you see the beams loaded pretty much as I discussed. Here you see the beam to column connection with the backing bars in place, both at the top and the bottom. And also here you see the panel zone that is instrumented because we're interested to measure the panel zone shear. So what you see here is that the story shear resistance of the entire subassembly at 2% drift doesn't exhibit any degradation. And besides panel zone yielding, which reached about 6 gamma Y in this case, there was only minor yielding in the beam flanges. But if you inspect here the region near the connections, you see that essentially the connection doesn't exhibit any serious damage that you would worry to repair. Now, if we keep pushing this to pretty much larger inelastic cycles according to the AISC protocol, what happens is that you see obviously that now you get a substantial yielding in the panel zone. The beams start to exhibit again flexural yielding, but again, notice that for a 4% drift that meets the AISC pre-qualification criteria, you get no degradation in the joints, and the panel zone is at 10 gamma Y, and notice that we get no fracture, although we have left the backing bars in place. And in addition, if I inspect the region near the beam flanges, you see that I don't get any buckling, so that would mean that repairs would be pretty much only associated with flexural yielding. Now, we kept testing this up to pretty much the equipment limitation. And what we saw is that, in fact, our objective to achieve stable behavior at very large drifts was actually met, which was actually quite interesting because that would mean that I have instability-free performance by leveraging shear yielding in the panel zone without exhibiting fracture as anticipated in these connections. And notice here that I am indeed above 15 gamma Y, and I'm already at a drift that is in the range of 6%. So basically here, we kept testing this, and ultimate failure mode in this case would be ultra low cycle fatigue, but that would only happen at drift levels that are well above the maximum considered earthquake and would be in a range that the system is not going to be governed by degradation, but the system behavior is going to be governed by big delta effects. So that would mean that degradation is not going to influence system behavior. So now, if we look at the region around the bevel backing bar, after the completion of the test, you see that I have no indication that cracks initiate in this region. And this match, in fact, our finite element simulation assisted design, which was encouraging to see when you introduce the bevel in the backing bar. Now, we've looked at this also with pretty serious continuum mechanics simulations where we assess the fracture potential by using micromechanics-based models to essentially find when ductile crack initiation starts, at what drift. And we did several material scale experiments with different geometries, as well as finite element analysis to kind of calibrate this test. And then by looking at scanning electron microscopy, we were able to essentially calibrate these models and essentially going back into geometries that are of interest to the designer, we were able to incorporate these micromechanics-based models and assess the fracture potential near the region where you have the bevel backing bar and near the region that we're usually afraid to have fracture. And based on our work, what we've seen is that, in fact, if you use some of these micromechanics-based models, ductile crack initiation would not commence prior to an MC level event. In fact, it would happen at a much larger drift in the range of 5 to 6% that I mentioned before, where the structural behavior is going to be controlled by P delta and not by crack initiation in this case. Now, with all this in mind, we looked at the behavior of archetype buildings to assess the impact of uh, uh, these sort of alternative mechanisms dissipating energy. And we looked at 32 steel buildings designed and analyzed in urban California that ranged from 4 to 20 stories. We looked at a different number of bays, like 3 and 5. And we looked at the variable panel zone shear distortions, where 1 being the elastic design, 4 being what is permitted by the code, and then we looked at 10 and 15 gamma Y designs that these are considered to be highly dissipative. You can download all the designs from, if you use here your cell phone, but they are also available publicly if you look at the paper. And the modeling approach here featured obviously the panel zone. That the model we used in the panel zone is a trilinear model that we predicted the parameters based on what I showed earlier in the first part of the presentation. Then we captured the potential of strength degradation in the beams as well as columns based on prior work that we've done in my group. And essentially here we are able to run simulations where what we can do is that we are doing model updating so that in case that the panel zone shear distortion reaches a very large value, so that would be 10 gamma Y. What happens is that we are setting the panel zone and the beam strength adjacent to that panel zone to have 0 flexural resistance, as if fracture happens at that beam. And this model updating is informed by this database I showed earlier, where we essentially computed this sort of probability of having fracture in the panel zone given a certain drift and a certain shear distortion. And essentially what we are learning from this is that if you're looking at an indicative case such as a 4-story, 3-bay mono-resisting frame, if you are looking at code-compliant design versus highly dissipative, and highly dissipative in this case would be a design that the panel zone goes to 10 gamma Y, you have a benefit when you're looking at the probability of collapse, that is being reduced by about 50%. But in my view, the biggest benefit is if you're looking at intensities that essentially impact the residual drift of the system, because as we know, when you're looking at code-compliant systems, we worry if this would remain at a large residual drift, and then potentially demolition would have to be imposed. So here, in this case, if you want to assess the potential of demolition, based on this analysis we did, we kind of collected residual drifts for all 32 designs. And if you essentially work in the framework of performance-based design, you can compute what would be the rate of having demolition by developing what we call demolition hazard curves by integrating the site-specific hazard curve over a residual story drift curve. And by doing so, what you can see is that if you are looking at design events with a return period of 475 years, the reduction you get on average on the rate of exceeding residual story drift ratios is about 30% when your design is allowing more panel zone shear distortion relative to what is code compliant right now. And also, if you're looking at different heights, you see that the residual drifts would actually reduce quite a bit. If you are looking again at return periods of 475 years, that in the US at least, this would be a design level earthquake. Now, this happens because simply if you look what the panel zone does, the panel zone is able to supply the system with a much more hardening relative to what the beams do, because shear yielding is known to essentially increase hardening in the system, particularly when also the contribution of the flange is important. Now, one or some of you may be interested in the case that you are using deep columns, and then in that case, if you have dissipative designs, what would happen in a deep column? Because with the current stability requirements we have for panel zones, you could see that you may induce buckling in the web. So for that reason, we essentially developed new web slenderness requirements for highly inelastic designs. And essentially the way we did this is that we kind of treated this as a plate problem, where we derived through stability theory what would be the corresponding stress at which you may have shear buckling in the panel zone. And then what we did is for panel zone geometries that could be crucial, such as those we use deep columns, allowing panel zone shear distortions in the range of 10 gamma y, we have a revised design rule that you should be able to use and achieve performance without exhibiting shear buckling in the panel zones. So I think I have about 15 more minutes or so. So I will shift the focus now away from the joint, and I will basically talk about columns. And so when I was in Canada, I worked a lot on columns, but also a bit after. And this is one of the tests we did back then with my first PhD student, Ahmed El-Kadi, in École Polytechnique Montréal. And here you see about 4-meter tall column, where here in this figure, you see the fixed end on the web and on the flange side. And here you see the moment rotation diagram synchronized under symmetric cyclic loading protocol. And what you see is that once you get to drifts that we anticipate at the design level event, the column would start degrading because local buckling again will kick in. And then because you have the axial load that is compressive, that would accelerate degradation. And what is more striking is that besides strength degradation, you are going to have axial shortening in the column because the gravity load is there and essentially doesn't go away. Now, this is a little different video that you can see how critical this could be for different geometry of a column where you get, it's again fairly slender, but still compact. And you see that once local buckling kicks in the fixed end, you basically have substantial axial shortening that you actually cannot control very well, even if you change cross-sectional geometries. And for instance, we've looked at also hollow sections that are interesting for Japanese designs. And you see here that you get, again, axial shortening that depending on the cross-sectional geometry, it could shift from conventional buckling mode 1, we call, to the elephant foot that you see here on the side. Now, if you think that this is something that is not happening, in fact, if you look at some of the reconnaissance done from the recent earthquake in Mexico in 2017, This is a three-story commercial building that was designed with box columns. And 4 days after the earthquake, you see that you already see the shortening happening because also you get unzipping here in the welds. But then 51 days after the earthquake, you see that the column has completely squashed. So despite the fact that, here we didn't have substantial horizontal residual drift, we had pretty substantial vertical residual drift, and still the building had to be demolished, although residual story drift was nearly zero. So for this reason, again, being provocative as I did with connections, we worked on rethinking of column-based connections in moment-resisting frames, and essentially, should we really do what we call strong base, weak column design, where the plastic hinge is forced to be in the column, or should we actually do something else if we are dealing with exposed column-based connections or embedded column-based connections that we talk about here? So I will talk more on embedded connections here, that usually in a traditional embedded column-based connection, if you design it so that the column will actually concentrate the inelastic deformations above the footing. What happens here is that when the column bears to the footing, you're going to get eventually local buckling near the fixed end that would actually concentrate right above the footing line. Now, to kind of tackle this issue, we developed the concept of a dissipative column-based connection for embedded to reinforced concrete footings, where here what we are doing is analogous to a buckling restraint brace. We weaken the embedded part of the column into the footing. And essentially, we foresee that the dissipative zone is going to be inside the footing, but only in the steel part. And essentially, it's concentrating in the steel part because, as we said, we are reducing the flange here. And what we do is that we are debonding the embedded part of the column from that of the concrete, so that when the column moves laterally, essentially you allow controlled rocking in the footing, and the footing actually works like a restrainer to the web of the column, so basically it doesn't allow the column to buckle. So this can be done with a filler soft material that could be styrofoam, and basically this could be the same material that we use in a buckling restraint brace. And because we are weakening what happens here in the footing, essentially we are allowing the dissipative zone to formulate inside the column at a lower moment than that above the footing. So the construction sequence here is pretty simple. Here you see how the filler material is being installed, and the reason why I'm showing this video is because we are not using any type of specialized construction. This was done by students, so we are not respecting any specific tolerances, or like we're not really looking into like a high precision manufacturing. Essentially, all we're doing is that we're cutting the region to embedded portion to the geometry we want, and then we are wrapping around with this sort of tape that it's analogous to what we use in a buckling restraint brace. And if you are wondering about construction sequence, essentially the column wrapped with this material is essentially installed and positioned with 4 anchors that are there for positioning. Then you install the reinforcement in the footing, and then you do the casting. And essentially the casting is, once the casting is completed, you remove the formwork, and then we're able to basically have the embedded connection as we used to have before. So we've tested this, And here you see tests on conventional bases as well as dissipative bases at the bottom. And here you see what would be the hysteretic behavior of the conventional base by allowing plastification above the footing. And here you see what would be the equivalent moment rotation relationship by actually employing dissipative base that is purely concentrated in the embedded part of the column. And what we see here is that early on, or when the drifts are relatively small, obviously both elements would exhibit yielding as anticipated, but the conventional base, once you get out of the 2% story drift ratio, it would start exhibiting local buckling here as intended that would quickly start developing axial shortening, whereas the dissipative one enables controlled rocking in the footing. And not only we can achieve stable behavior to a drift that goes beyond 8%, but also we can eliminate axial shortening that is actually a pretty big issue as we saw before. You might be wondering what this damage, so this is damage that is happening only on the cover of the footing that generally can be fixed simply by basically recasting that part, which is not more than a few millimeters. We know this because we did section cuts with a diamond saw blade into the footing to inspect the actual footing. And here you see that for surface 1, there is no indication of damage in the concrete. Surface 2, the same, which is adjacent to the embedded part of the column. And also, if you are looking surface 3, notice here on the upper part that this is the only part that was damaged that is related to the cover. But then when you're looking at really into the footing, essentially there was no cracking in the footing. We verified this concept with conventional finite element analysis, where you see here one of the models. And in fact, this model demonstrates that damage indeed concentrates within the dissipative part of the column, only in the steel portion. And then here, what is quite interesting is that since I don't have instabilities in this case, you only rely on capturing well material nonlinearity, which is something that we do well, at least with conventional constitutive models. So that takes away the uncertainty associated by imperfections, welding, and other aspects that could control instabilities or could induce weakening in the columns. Now, we looked at, through finite element analysis, we looked at different geometries, different loading conditions. We looked at different protocols. For instance, here, we're looking at the case where we contrast the dissipative base with the conventional base. And you see that even at drifts that we're anticipating at the maximum considered earthquake, we get no degradation for the dissipative base, but also we get no axial shortening or very minor axial shortening because of accumulated plastic deformation within the dissipative part of the column. That is considerably less than what would you get if you allow local buckling in the columns. And essentially, if you are looking at the deformations of the column near the end, in one case, you end up having substantial column axial shortening, whereas in the other one, you basically have only localization because of yielding that essentially you allow in here. Now, we've looked at also alternatives for exposed column bases, where instead of allowing plastification again in the column, you basically allow plastification to happen in anchors. And in this case, if you are careful with the way that you are basically designing the anchors, you can essentially remove the anchors and install new ones. And that would allow to have what we call a self-centering response without using a complicated fixture here at the base, by only simply allowing yielding happening in the anchors. Essentially, you can achieve a self-centering response. Before I wrap it up, we've done also some building performance evaluations where we compare a conventionally fixed base design for a design level earthquake, the maximum considered earthquake, versus that done with a dissipative base. And here we are looking into cases where response duration could be very important, such as Oregon, or like if you're looking at Vancouver, Ireland, where you may get ground motions where response duration could be quite substantial. And here you see that both for the design basis intensity out of a 44 ground motions that we used, as well as a fixed base at the maximum considered earthquake, you see that I can literally minimize axial shortening to almost zero, or literally zero, in both a design basis earthquake as well as a maximum considered earthquake. So if I want to summarize what we saw, the first thing I'd like to say is that hopefully rethinking the seismic design of steel moment resisting frames could be something that can be done, but I must say that there still needs much work that needs to be done. Hopefully you were convinced about the beneficial aspects of energy dissipation through shear yielding. We saw two concepts, that the first one related to connections, that we can achieve instability-free performance up until very large drift demands that would be 6% or higher. That could reduce reliance on complex models, such as the ones that you've probably seen from me, to trace strength degradation mechanisms, because simply they would not happen at drifts earlier than 6%. You can also greatly reduce residual deformations, both at the story and member level. And we also saw some concepts that this can be achieved that retain design simplicity. One was the welded connections with highly dissipative panel zones. The second one was dissipative column-based connections that essentially allow weak bases. And what I'd like to stress is that in these concepts, these are not concepts that you would leverage dampers or other type of high technology. These are concepts that essentially the designer would simply use alternative design checks and would just shift the energy dissipation mechanism from, let's say, one location to another, essentially simply by following capacity design rules again. So with that, I'd like to thank you very much for your attention. And hopefully this was interesting, and I'll be happy to answer to any questions.
Thank you so much, Dr. Lignos. I would like to open the floor to our participants. If anybody wants to ask a question, they can raise their hand. I can let them unmute, or they can type in the questions in chat box and I can read them on behalf of them. I have already one hand raised from Ali, and then Mariam will be coming afterwards. Ali, please unmute yourself and you can ask your question.
I think we have to let them unmute. I think now you can unmute yourself.
Yeah. Thank you, Professor Lignos, for the interesting presentation. My question today comes to the material scale level. When I was working in the structural lab at EPFL, I saw the scale of your experiments, which was very interesting. But as I said, I want to ask about the material constitutive modeling. When it comes to a new material constitutive modeling, what would be your strategy to validate this material scale model in a nonlinear finite element model for full scale element? Is it like we find some experimental data in the literature and then we go and model it for a nonlinear finite element model, and then we validate our constitutive model? Or I'm very curious, what is your strategy to validate that material scale model in a full scale nonlinear finite element model?
Yes, yeah, this is a good question. So, and also this relates to the fact that, if you are doing this well, then you basically only rely, you will only have to worry about uncertainty associated with the material model itself. So to answer this question, I will escape the presentation because I'd like to show you something else. And then basically with that, I will answer the question that you are asking. So give me a second to stop sharing. So if you use a constitutive model, and let me open what I'd like to show you. So if you use a constitutive model such as that we use in typical finite element software, you would have to essentially capture the primary characteristics of the still material. That would be a combined isotropic kinematic hardening. So that would mean that you need a constitutive law that does this. Okay. So if you look at commercial finite element software such as Abacus or others, these models are available, and so then you would need material scale experiments to be able to calibrate this law. Now, we've looked at this problem very, very carefully, and if you basically come to this website I was advocating before, which is, we call it reslabhub.epfl.ch. Here, essentially, you are getting databases on connections, columns, braces, and materials. So if you actually click on materials, you will have access to data sets at the material level that essentially will involve all structural steels that you would have pretty much worldwide, including US steel, Asian steel, as well as European steel. And you are able to download this if you want. Now, if you go to the material model, if you click, so for instance here, if I'm interested on, let's say, one of these experiments that I will pick one that I happen to know, give me a second, that essentially uses well, it doesn't matter, I will pick one. You see that what we've done here is that we are giving you, for any kind of steel you want, the associated data, but also material models that you can use, material model parameters that you can use directly in your finite element model. And essentially, you will have a pretty good prediction of your constitutive model when it comes to using it into a finite element environment. Now, if you click here where we say material model, I'm not sure where it doesn't go, or it doesn't like to go. Anyways, maybe there's something wrong with the way I'm setting, but if you click at the material model, essentially, you will get a list of different steels where essentially what this list does, it gives you reliable parameters that you can use directly in a finite element environment that is actually based on this material database that I showed you. And based on our experience with this problem, we think that this could be quite sufficient, provided that the kinematic isotropic hardening in structural steels is controlled by chemical composition. And if you are looking at, say, A992 grade 50 steel or others, usually the composition doesn't vary a lot if you ask a steel making company. In addition, it's controlled by the way that the steel tubes are produced. And again, the steel making company will have this quite well in terms of quality control. So using a set of parameters for different steels that we provide here, we think that that would give you a pretty good validation of your constitutive model without having to do complementary tests. Now, going back to my presentation, as I mentioned to you, we've looked at some of these validations at the finite element scale. Let me just try to go back. When we were working with these sort of columns that I showed, and some of you, can you see my presentation, or you're looking at the presenter mode? Some of you may be familiar with some blind analysis competitions that were granted from the National Institute of Standards and Technology, where we use this type of methodologies on model calibrations and so on. And we were able to successfully reproduce the behavior blindly of different elements that were tested simply by using some of these things that I showed you.
Yeah, exactly. That was my point as well, because you talked about the parameters and I would say phenomenological constitutive modeling, like the classic ones, which works with the calibration and the parameters. But when it comes to a purely data-driven model, it doesn't need the parameters, and it's just calibrated with the data itself.
Exactly.
It's kind of, I don't know, challenging to compile it to a nonlinear finite element procedure. Because it's like in a material scale, and the uncertainty I'm interested is in material scale. But when I go to the modeling, there is a couple of uncertainties in other levels, like for example, in the OpenSys procedure, in the section constitutive behavior, in the elements I choose. So if you can, I don't want to waste the others' time, but if you can shortly guide me in how you control the uncertainty to see what's the behavior of what you're interested in this procedure, like the material behavior.
Yeah.
To control that.
Yes, maybe I can answer this in a brief way. So the way we treat this problem is that we break it down. So if we talk about finite element or OpenSys, essentially the way we treat this problem is that we think that you have to consider a constitutive law that is calibrated properly, and I showed you how.
Mm-hmm.
Then you have to consider imperfections in your finite element model so that you can trigger buckling at the right time. And on that, again, we have provided a pretty detailed studies into what imperfection amplitude should be. In particular, we have shown that, for instance, if you are assigning imperfections in the range of d over 250, d being the web depth of your member, and bf over 250, which is the flange width of your member, then you can actually capture the onset of local buckling pretty well. And then the third ingredient you need is a residual stress model, because there could be cases where lateral torsional buckling could be controlled by residual stresses. And for that, again, we have a residual stress model that you could use without having to worry about this. Now, if you're looking at OpenSys, as you said, discretization would be important, but usually discretization is important if you're dealing with softening, because you get strain localization. So in this case, if you are using, let's say, fiber-based model, not like a continuum model, basically I would have to be careful to either use a regularization scheme with a given discretization, so that I can alleviate the mesh dependency I'm going to have. So that, in short, if you are interested, you could also send an email, and then I can also guide you with some literature, including specific details on how you can tackle the same problems.
Yeah, thank you so much. That is what I regret to not ask you when I was at EPFL, but I will email you for sure. Thank you so much.
I guess Ali is just realizing the the distance is a factor. Sometimes being close is better, but the technology is there. We'll be really happy if you can connect with you through the email or through other platforms, and hopefully Ali will be able to reach you, and then you will be able to answer his questions through that.
Thanks for answering, though. Thank you.
Thank you. The next question, Dr. Golestani, they raised their hand, and please unmute yourself and you can ask the question.
Perfect. Thank you so much. Such an work. I enjoyed the presentation.
Thanks so much.
Slide 8, we're talking about this zone and everything.
Slide 48. So your voice is chopping a little bit, but if I understood correctly, you were asking about slide 48?
Yes.
Yes.
The bond material you mentioned, if it's generally done, you do it because they don't want the damage to go into.
Dr. Golestani, sorry for interrupting. It is intermittent. I really cannot hear what you were asking. Maybe you can type in chat and I can read it for you, or you can just try to.
Sort of your voice is chopping a bit. And I understand you are asking something about the debonding layer, but it was hard to understand the question because it was chopping. But if you type in the chat, we can try to answer.
All right, thank you. So there's another question. There's actually a couple of questions right now in queue. I know that it's getting late, so we will try to stick to the proposed timeline. We still have 12 minutes more. Dr. Ramzadeh is the next question. Please unmute yourself and you can ask your question.
Okay, thank you. Thank you very much for very nice presentation, very informative. I have several questions, but I understand we don't have much time, so I get to the one that I know better. So I noticed when you were showing the material modeling in your website, I noticed you, for the material constitutive modeling, you use 2 back stresses. So that's something, I think it's going to be a long discussion, but I keep that aside because what I've seen, they usually three back stresses. And one thing that I want to ask you is about strain rate effects, because in many, I believe in your experiments, you did mainly quasi-static testing. And in some of in finite element models, then later on when you did nonlinear time history, in some cases you did nonlinear time history analysis. Based on my experience, kinematic hardening doesn't change much with the strain rate, but isotropic hardening might change a lot because of the heat effect and stuff like that. But I want to know whether you considered the strain rate effects in your models.
So first of all, regarding the first part of the question related to the number of back stresses, so we have looked at this and we have repeated calibrations with 2, 3, and 4 back stresses. So if you're looking at the material scale, so stress strain, right, then you are right that you will see some difference. But if you're looking at the impact your number of back stresses would have in predicting the member behavior, basically we've seen that above 2 you get no difference. So this is why we're considering 2. But if you look at one of our articles that essentially discusses about the calibration procedure and number of back stresses, we also saw that if you use above 2 back stresses, at least with the way we do the calibration, then you're not going to get reliable input model parameters when you go above 2 back stresses. Now, with regards to strain rate effects, this is a very interesting question that you are asking. We have looked at strain rate effects at the material scale. And in fact, if you consider by doing material scale tests quasi-statically, but also by considering actual rate that you see in an earthquake. And we measure also the heat that is generated within the material scale with thermocouples. So what we've seen is that indeed some of the components related to hardening will be influenced. But if you don't use rate independent plasticity, which is what we are using, and you use a material law that essentially considers rate dependency, that should be no problem to capture this. Now, how does this influence the overall structural behavior? This we haven't looked, but that's certainly something that is worth looking. My impression about this would be that rate dependency is for conventional systems like moment frames will slightly impact maybe the onset of local buckling, because since you have more hardening, most likely buckling will be delayed a bit. But the overall behavior that we see should not be very, very different. I think you and I know, like, your advisor also at the UBC, you've been working with shape memory alloys.
Yes, yes.
And in shape memory alloys, because they depend on temperature, or their behavior obviously would be influenced by temperature. This is something that I think worth investigation when you are looking at rate effects. And that's something we've seen at the material scale, because in some of these tests I showed, in fact, we do have test data on shape memory alloys, but more like iron-based shape memory alloys.
Yeah, I've seen that publication.
Yes.
Very nice work.
So I think maybe there is one question. First of all, regarding my presentation, as I stated at the beginning, I'm happy to share the slides.
Okay.
And I'll send those right after the event, because I think there's one question related to this.
Okay.
And then there is one question related to repairs if you allow plastification in the panel zones, and what would happen in the column-based connection. So I think the way. So first of all, the way that we have to think about this is the following. When we look at conventional systems such as moment frames, we have to think what we would do today if there is damage in the beams that will trigger local buckling, and there is damage in the columns that would trigger local buckling in the column at the base. So assuming that the residual is not going to be large, then you will have to use some sort of heat straightening technique to kind of repair the beam and repair the column. But that would mean that you need to basically have a contractor to do this. You need to shut down the building, and potentially, of course, you're not going to allow functionality to be, because simply you will have to do the repairs. Now, with what I'm suggesting, assuming that the residual deformation is not going to be large, so this would mean that there's not going to be demolition. If you have CR yielding evident in the panel zone, CR yielding is a stable energy dissipation mechanism, as we showed. So assuming that your drifts are modest, in one case you would do repairs in the beams because you would have onset of local buckling, etc. In the other case, you would probably have to do nothing because you would have a panel zone that just experienced yielding, but then you see that yielding can carry on till very large drifts without having to do anything. Now, with regards to the footing, again, assuming that the drift range is somewhere between 2 to 4%, the debonding layer should be sufficient to kind of having an aftershock, or even having a second design basis earthquake. But of course, if drifts get much larger, then I don't think you would worry about not demolishing or not, because at the end you would have a system that would have a very large residual either way. So I think with what I'm suggesting, obviously this is not a high performance system. We're not using dampers and so on, but with what I'm suggesting is that if there is a chance to minimize repairs, this would be that. And if there is a chance that you're going to end up having less residual, again, this would be that. Now, I think there was a question. I'm
Yes,
sorry.
thank you, Dr. Ignos. There's Dr. Golestani submitted their question by chat, and actually I'm going to combine, if there's no other questions from our participants, I would like to add from my side a question combined with Dr.
Yes.
Golestani's question. It is about the question is the debonding material used because you don't want the damage to extend deeper into the concrete, or is it just general practice? This is their question. My question is actually when you presented, especially for the dissipative column bases that are embedded in the concrete, you show the construction sequence, but the way how it's constructed, my understanding is you embed, you connect, and then you bring the reinforcing of the footing afterwards. For an individual footing, that really works well. We can clearly see that from the demonstration. But if you have a different type of foundation system where you have continuous rebars that has to go through the foundation, how you see that? Is it a problem to in terms of constructability? Is there any other alternative that you envision that to make that system work if there's a challenge out there?
So to answer the first related to the deboning material, so the deboning material we need because we would like to minimize friction between the column, the embedded part of the column, and the concrete that is around the column. Because if we minimize friction, essentially, we're not going to rely on bearing of the column against concrete. And similar to a BRB, as I said, you're going to have the column kind of work as the footing work as a restrainer to the part inside the footing that is supposed to dissipate the energy. Now, so generally, yes, you will have to have a debonding layer so that the friction is going to be minimized. Now, with regards to the second question you have to the constructability, obviously, if you have a system that you have, and I don't have these photos, you have kind of like a not individual footing. Obviously, in this, yes, obviously in this case, there has to be the construction sequence has to take into account this. And I have some photos where embedded footings were used as a retrofitting scheme, in fact, by taking into account what you are asking. And it is true that you have to basically think about how the reinforcement is going to be done, but it's what I'm trying to say is that it's not impossible to be done. But of course, this is configuration specific. Alternative to the embedded would be the exposed, but then when systems get taller, usually you would like to go the embedded footing so that you don't end up having like a unrealistic base plate thicknesses that would potentially be a problem to get.
My apologies if I missed that part, but is there any requirement for the embedment depth for the foundation to have the system efficiently work?
Yes, so here I didn't show this. Usually we would have an embedment depth that is in the range of 1.5 times the depth of the column. But this is not different from what is done today in terms of, let's say, embedment depths. So in that sense, this part is more or less the same with what would you do today.
All right. I'm looking at the chat box and I'm looking at the participants. There's no more hands raised. I know it's 7:30 over there, and we don't want to keep it too late. It was an interesting and riveting, unintended presentation. On behalf of Green Construction Research and Training Center and all our participants, we would like to thank you so much for your time. Thanks for this presentation, you sharing your time with us. As you mentioned, after the event, we'll be looking forward to receiving your presentation slides in any format, if you can share with us, and I'll be communicating with our participants. And if there will be any questions, will you be okay them sending directly to your emails, or you want to act as like a connection point to make that happen? Will it be okay?
Well, thank you so much as well. It was a pleasure. And as I wrote in the chat, Thank you, everybody. And, I'll be happy to answer to any questions. Feel free to email me. And hopefully, we can see each other in person at some point.
Thank you very
There's
much.
Thank you so
Thanks
much.
so
for
much.
your
Thanks,
time.
everyone. That being said, this is the end of our seminars. Thanks for everyone for participating.
Thank you.